let's talk about example B from spectroscopy. For example, well, let's take NMR. In order to interpret an NMR spectrum, spectroscopists use a spin Hamiltonian. And the spin Hamiltonian is one example for something one could call or calls effective Hamiltonians. And effective Hamiltonians are when you sort of focus only on a selected number of variables and you have hidden all the other variables away. So in the spin Hamiltonian, which you use to interpret an NMR spectrum, the only variables you have are the spin of the nuclei and the magnetic field. So, but you still sort of, that's a spin Hamiltonian for a particular molecule. NMR spectrum of whatever, ethanol. Proton NMR spectrum of ethanol. Of course, you still have all the electrons with their spin, with their position coordinates. You have the position coordinates of the nuclei, but they are all hidden away when you use an effective Hamiltonian, a spin Hamiltonian. So a spin Hamiltonian for NMR spectrum would look like this, where we have a sum over all nuclei A. We have the spin of that nucleus, the spin vector of that nucleus, which interacts with the magnetic field, the external magnetic field. And that is nothing else than the expression up there. This one. So we're missing something because in here we have a few parameters. That's the nuclear G factor. That's the nuclear magneton divided by h bar. And all that together is actually the magnetic, do I use mu m? I think I use m. Yeah. That is the magnetic moment, the magnetic dipole moment of nucleus A. So it's precisely like up there, minus dipole moment field. That would be, without that parenthesis, if we would have a nucleus alone in the magnetic field. No electrons, no other nuclei, just this particular carbon 6+ nucleus in the magnetic field, then this would be the expression actually for the energy and or for the Hamiltonian of that spin system, where we only look at the spin. But I mean, obviously there are electrons and there are other nuclei in the molecule. So this expression is then modified because what we really have to look at is the local field at the position of that nucleus. If you have just a nucleus alone in a homogeneous, very nicely homogeneous magnetic field from a big magnet, then of course the field of the magnet and the field at the position of the nucleus are the same. But if that nucleus already has electrons, so it's not carbon 6+, but the carbon atom with its electrons, then they are no longer the same. Because now I have electrons, and the external magnetic field is going to, and electrons have a charge, so we have charges in fields, and charges in fields gives rise to induced moments, which sort of classically obviously oppose the external field, and in quantum mechanics it can be both ways. So there's some kind of a screening of the external field. So the local field is different, and you write that by introducing this shielding constant, or in general a shielding tensor again. The local field doesn't have to have necessarily precisely the same orientation in space as the external field. So you have the shielding due to the electrons. But we can also have other nuclei with spin in the same molecule. And if you have a nucleus with a spin, you have a magnetic moment. That magnetic moment, of course, leads to an extra magnetic field. So we get an extra contribution to that, where another nucleus, let's say B, B, due to its magnetic moment, due to its spin, produces a magnetic moment. That magnetic moment generates an extra field at the position of nucleus A. Now that extra contribution, in principle, you could write up like this, but it is written up in a slightly different form. So we get an extra contribution, a sum over, well, all the nuclei A and B, the other ones. And again, there's this A smaller than B or A larger than B, because you only want to have each interaction counted once. And then this is directly formulated in terms of the two nuclear spin. In the way I looked at it now, A, this one being perturbed by the other spin, or at least the field at this one being an extra field generated at this nucleus by this nucleus, but of course, I mean, it's vice versa. And there's a coupling constant between them, which is also a tensor principle. And then we have the constant, 2 pi over h bar. So in general, I mean, what is standing here is the analog to E, the analog being operators for Hamiltonian, but the energy expression which is lying behind there is just minus magnetic moment with m of nucleus A and times, being a vector, times the local field at that nucleus A. And here we have the local field there, and you also can sort of consider this by multiplying with appropriate constants, this as an extra contribution to the local field coming from the other nucleus. Now, none of these, so the molecular properties we have in this spin Hamiltonian for us, obviously here the shieldings, and here this spin-spin. Spin-spin coupling constant tensor. For the NMR spectroscopist, these are just parameters they fit. Because what they do, I mean, this is Hamiltonian, so they know what kind of spins they have in their molecule, so they can set up a basis set of spin functions for describing that. If they have two spin 1/2, for example, if you take water where you have 2 spin 1/2, you have and all the ones who had chemical S, you all did that. You have a system with 2 spin 1/2, which gives you a 4x4 matrix of this Hamiltonian then. But in doing that, and then you can calculate what the eigenvalues are of the energy, the eigenvalues of the Hamiltonian, the energies, and you can calculate what the transition would be and find out which transitions are allowed. And then you get expressions for the energy change on the transition, and they still contain those parameters here. And then what you do in NMR spectroscopy, you fit the calculated energy terms, energy differences, energy frequencies, you fit to the experimental ones, and in this way determine those parameters. So for them it's just fitting parameters. But for us, those are the molecular properties which we can calculate and do calculate.